Can I start, sir?
No, I will tell you. Just wait.
Okay.
He is enabling live streaming now.
Preetham, you can start.
Okay, sir. A very good morning to all of you. Now I am going to introduce our next speaker, Dr. Siddharth Panda. He is going to give a lecture on enhanced performance in ion selective field effect transistors. Dr. Siddharth Panda, presently working as a director and professor in the National Center for Flexible Electronics, IIT Kanpur. His research focuses on chemical sensors and the accompanying transport reactions and materials processing, utilizing silicon and flexible printable platforms. Prior to joining IIT Kanpur, he was a staff advisory engineer at the IBM Semiconductor R&D Center, New York, for over 6 years. He has 60 publications and 33 patents to his credit. He was awarded IBM Invention Achievement Award 2002 to 2006 and G. Blinder Research Fellowship 2010 to 2013. He is the member of American Institute of Chemical Engineers, Semiconductor Society of India, and the Society for Information. Now I am requesting Dr. Siddharth, sir, kindly proceed.
Thank you for the kind introduction. Just one clarification. Here we say
Yes,
we use the word coordinator instead of director for a center.
Yeah,
But anyway.
yeah, I was just thinking.
Okay.
We are sorry for that.
Coordinator.
No problem. Just wanted to check. So I'm just sharing the screen right now. Just give me a couple of minutes here.
Yes.
Yes. Yeah. Perfect.
It's indeed a pleasure to share the work from our group among peers in the field. And I would like to thank Professor Grace for this invitation. And I would like to congratulate VIT for organizing this conference and giving us all a platform to share our works. My name is Siddharth Panda, and I'm going to talk about enhanced performance in ion selective field effect transistors. So now what are ion sensitive field effect transistors? Well, if you see the picture here, schematic here, it is again, it is just a transistor, except that we, instead of a gate, this gate electrode, that is replaced by an electrolyte. Everything else remains the same. We have the source, we have the drain, and then we have the path in a, the electron path in a semiconductor. Now, what happens is that we have an ion selective interface here. And when there is a reaction between the electrolyte and the ion sensitive interface, a reaction happens, a chemical reaction happens, which results in the generation of a potential. So this potential acts as an equivalent to the gate potential, and this potential modulates the transport of charges between the source and the drain. So what can be done here is that if we have a given chemical reaction happening, now we can map the potential which is generated through the measured electrical characteristics to find out what is the extent of reaction which has happened. And the extent of reaction is now proportional to the concentration of the reactants, and thus the concentration, the type of the analytes and the concentration of the analytes can be measured. So in a nutshell, this tells us how we are able to measure, how we are able to measure the concentration of analytes in an electrolyte with the help of a transistor. This ISFET is a component which can now become a part of a larger device, a solid state device out here. And these have several applications. For example, in the medical field, these can be used for diagnostics. In the agriculture sector, they can be used for testing the quality of the soil. In the environmental sector, these can be used to test the quality of water, not only drinking water, but also industrial processing water. And similarly, in the food sector also, it can be used to detect the presence of several types of analytes. Now, if you look at these analytes, this can range from a very simple ion like that of a hydrogen ion, and all the way to complex charged biomolecules. So what we have seen in the literature, what we can find is that like these kind of devices have been utilized to detect simple analytes to all the way to complex analytes. And in our lab also we have done the same, and I'll be sharing some of the work which we have done in this regard. So now let us look at the glass electrode, a typical glass electrode based pH meter, the schematic which is shown on the left hand side of the presentation slide, and compare it with the ISFET based pH meter, and for which a typical photograph from a commercial product is shown here. So these are the different parameters. And then what we do is compare the glass electrode based system with the ISFET based system. And the ISFET pocket based system is a smaller system. I will not read out all the parameters out here. What I would like to say is that the ISFET has several advantages. For example, it can be produced on a much larger scale, and which now brings up a cost advantage. At the same time, the time constant is much smaller, and more importantly, the conditioning is not needed. However, there are also some limitations. For example, encapsulation is critical, and also there's a limitation as far as the temperature range is concerned. But there are a lot of application areas where this ISFET can be used, and the advantages are making it all the more attractive. And hence, there is a need to further understand the different parameters, especially the performance parameters, and then have a basic understanding how to improve them. Now let us understand some of the performance parameters. One of the performance parameters is sensitivity. So utilizing these kind of systems, we can not only measure the ions of interest, for example, with a hydrogen ion or charged biomolecule, but also it also can be utilized to measure some ions in an indirect route. And let me elaborate. For example, like if there is a certain molecule which may not be electroactive, but this molecule can now be tagged to an electroactive material. So then by measuring the electroactivity of the tag, one can be able to map what is a concentration of the analyte of interest. Also, in several applications, we also need a standard, and hence it also becomes critical to have a very high sensitivity so that we are able to differentiate between the control and the experimental conditions. Now, when we look at sensitivity, let us understand what are the factors that affect sensitivity. Now, if you look at a typical semiconducting system, if you take a semiconductor device, we have the semiconductor, we have the insulator, and then we have the electrolyte, as we saw in a previous slide. So one of the factors which affects the sensitivity are the properties of this insulator. And we'll talk about that even in more detail later on. Then we have the semiconductor insulator interface out here. And one factor is the density of the interface states. We also have the insulator electrolyte interface out here. And some of the factors involved are the density of the surface states and the types of surface sites. So now, having looked at the factors which affect sensitivity, let us look at the means to enhance the sensitivity. So there are different methods to enhance the sensitivity, and some of these are listed below. One is to use high-K dielectrics, the insulators, and also stacks instead of single materials. Another way is to use this nanostructured dielectrics in semiconductors. And also another way is to come up with newer device designs. Now, let us have a brief review of these three methods to improve the sensitivity. So this shows a table of different dielectric materials and the sensitivity which has been obtained. This is in the ascending order. So typically what happens is these materials have a variation in the buffer capacity, and because of which they have different sensitivities. Now, there are also reported works on utilization of this nanostructured semiconductor dielectric materials to enhance sensitivity. For example, in the one particular case, silicon nanowires were used, and the silicon nanowires, and then they were coated with this dielectrics. And what was found that because of this utilization of the nanowires, the sensitivity increased from about 55 to about 60 millivolt per pH. In another work, again by coating this aminosilanes along with the zinc oxide, nanowires, again the sensitivity was enhanced. And coming to device design, and there was a paper in 2012 which started this work on the utilization of the dual gate structures in this ISFETs. And by utilizing a second gate, the sensitivity was enhanced from about 48 millivolt per pH all the way to about 380 millivolt per pH. What I'm going to present is some of our work where we have again utilized these three philosophies to improve and enhance the sensitivity. So first we start with utilization of nanostructures, that is more specifically silicon oxide nanoparticles, and also functionalization to enhance the sensitivities, and we have utilized an electrolyte insulator semiconductor system. Just to give an analogy, this is like a diode instead of a transistor. So what we did, this shows the schematic of the device used. We have the semiconductor, then we have the dielectric or the silicon oxide. Then what we did, we aminerated it utilizing this APTES. And then what we did, we dipped this particular this wafer in a sol where the silicon dioxide nanoparticles were being synthesized. And I'll talk in more detail in a subsequent slide. So what we have is, we have this SiOH, and we have then this binds with the amine group, and on the basis of this, what we see is that we have this formation. We have the silicon nanoparticles which now form on this surface. So what we saw here is that we had the control case, which was a planar device that we did not have any texturing. So that gave a value of about 37 millivolt per pH. But then what we found was, when we added particles, we saw that the sensitivity went up. And also what we found is that smaller the size of the particles, higher is the sensitivity. So what we saw that there were two factors which were affecting which were the reason for the higher sensitivity. One was the particles, and more important, particle size, and another was the surface functional groups. So we wanted to study that further, that how can we utilize this nanotechnology in order to further improve the sensitivity of these devices. But before that, we looked at the processing of these nanoparticles, because the manner in which the nanoparticles are made to immobilize on the surface is very critical for the performance. So this then we had conducted a study on the dielectric surface texturization and the different mechanisms. So in a typical process, like a Stauber's process, when we have this synthesis of this silicon nanoparticles, and we can control, by controlling the parameters, we can control the ultimate size of the particles. So this particle size evolves as a function of time, and this is what we have seen here. And this shows the SEM of a typical result after it has stabilized. Now, while this sol, in the sol, as the particles are growing, what is critical? What the criticality? What we found was, at what point do we insert our wafer in order for the this texturization to happen. And that we found plays a very critical role. And second thing is that, like, for how long do we keep it? And that thought process is shown here. That, okay, at what point do we wafer is introduced into sol, and at what point is it removed from the sol? Now, what we found was that we want to have a high density of particles, because as we see later, that higher density of particles will help us give us an enhanced sensitivity. Now, the particle density, what we found, depends on the time of introduction. And the time of introduction depends on the mechanism, what is happening in the growth process of the particle. When we have this growth of particles, it typically passes through three phases. One is the induction phase, and then is a nucleation phase, and finally is the growth phase. So we conducted experiments, and what we found that when we were this introduction of this wafer at the nucleation stage was critical to give the highest particle density. And all the details are provided in this particular paper. But to say this in brief, this is because of the interplay of the homogeneous and the heterogeneous nucleation. So having understood the mechanisms which played a role in getting the maximum particle density, then what we did was we wanted to understand further why do these nanoparticles help us get higher improved sensitivity. So we conducted these CV measurements, and then what we found was that this showed an hysteresis which was not there in the MOS systems, and this is because some interface traps were formed. So what we see here was that when we have salinization, that is when we put this APT here, there what we see is a shift in the voltage in a negative direction, because we have got positively charged entities out here. And then next step is when we put the silicon dioxide particles out here, then what we see is again a shift in the positive direction, and that is because this NH2 this amine sites are now covered with the nanoparticles. So these results, we wanted to understand these results, and that helped us understand what was happening at this interface. Similarly, what we saw, we also conducted the zeta potential measurements, and we found that the zeta potential measurements were consistent with what we saw with the electrical measurements. That is, when you had a planar silicon dioxide, we had a highly negative zeta potential, but when we aminated it, it became positive, and in we texturized it, it came close to zero, and that helped us understand what was happening at the interface. Then what we conducted this absorption studies as well as photoluminescence studies. And what these told us, and these were done for these different kinds of wafers. That is, we had this planar wafer, salinized wafer, and the wafers which were textured with particles of different sizes. So what we learned from here is that when we had the particles, when we textured on the surface, that is for a textured surface, there were increased number of defects, and these defects were responsible for the enhanced buffer capacity, and that helped obtain a higher sensitivity. Then again, from the CV measurements, what we saw that, like as I mentioned earlier, that we were able to understand the effect, that how the capacitance, why the capacitance went down, because once we added salinization is again because of dielectric constant of this APTS layer, which are again almost like the order of nanometers. I mean, that is the thickness. And again, we saw that the negative flat band voltage shift was because of this amine layer. And then once we had this texturization, there was an increase in capacitance because the surface area went up, and so on. And also we looked at the positive flat band voltage shift because of this different steps. So the learning from here is that there were several complex phenomena which are happening at the interface. This hydroxyl groups and the amine groups played a very critical role. And what we learned was that there was an optimum ratio of these two groups, and that was responsible for getting the highest sensitivity. So having seen that, We wanted to verify this learning by using another form of nanostructures that in this particular case, instead of silicon nanoparticles, we use zinc oxide nanorods to see whether we are getting a similar behavior or not. So without going into too many details, what I would like to say is that when our base value or the control for the control device was around 37 millivolt per pH, but when we had this zinc oxide nano rods, it went up to about 50 millivolt per pH. So, and then what we did, along with studying the detection of a very simple ion, that's hydrogen ion, we also looked at complex charged molecules. In this particular case, we use the system to look at an antigen, anti-PSA. PSA is for prostate-specific antigen. So what we had on the surfaces, we had put antibodies and we put antigens in different concentrations, all the way from 1 nanogram per milliliter to about 100 or 1000 nanogram per milliliter. And then what we found is indeed there was a voltage shift, which means we could utilize these devices to measure or detect these antigens which are present in the solutions. And what we found was indeed there was a signal shift, in this particular case 23 to 35 millivolt. And what we saw was that such a device also could measure complex charged molecules. But where the sensitivity is higher, I'll talk about it a little bit later in this talk. So what we saw, we saw two examples of using nanostructures. This one was a nanoparticle and one was a nanorod. Next, we looked at nano-coatings. So what we did, on the surface of the dielectric, what we did, we now used branched PEI, the structure of which is shown here. And this is a schematic of the device which was used. And this is a schematic of the electrical double layer, which is now formed at the interface of the electrolyte and the solid surface. And this EDL plays a very critical role. So for the control, then these are CV measurements. One is for the controlled device, which is in green out here, and one is for the device where we have put this nano coating. This is which is the branch PEI. So again, the results what we saw were consistent with what we are expecting. That one case that the capacitance went down, and that is because of the dielectric, the dielectric constant of this particular layer. And also there was a slight negative shift in the voltage because of the positive charges which are there on the amine groups. But then our interest was in looking at the sensitivity. So in this particular case, the base or the control device had a sensitivity of 24 millivolt per pH. But by adding this coating, nano coating, we saw that we are able to get a higher sensitivity, which is about 110 millivolt per pH, which is almost 4.5 times, 4.6 times. So what this shows now, another advantage of using this kind of a layer is not only we can utilize for measuring the pH, but also we can utilize for measuring more complex charged biomolecules. So what we have done here, we have seen here that we took a device by putting by functionalization, we are able to see an enhanced performance. Then next what we did, we took the same device, and then what we did, we changed the architecture of the device. That instead of a electrolyte insulator semiconductor board, which is like a diode kind of a structure, now we made it a transistor kind of a structure. And in this particular case, we use an electrolyte gated field effect transistor. That is, we do not have a dielectric, but in this case, the semiconductor itself is used for sensing. So now what we did, we took this semiconductor here, which is IGZO. But then there was a process optimization which had to be done, that we had to optimize the right annealing temperature. And this is something which I'm going to talk in a subsequent slide. What is the role of annealing? Because this process conditions become very critical. So what we found that 400 degrees Celsius was the optimum annealing condition. And then again, we measured the sensitivity out here. And what we found that by changing the device architecture, the mode of measuring it, we found that it increased to 160 millivolt per pH. So just to recap, the base device in this particular case had 24 millivolt per pH. Now, if we add a nano coating, we went up to 110 millivolt per pH, and then by changing the device design, we were able to go to 160 millivolt per pH. Then coming back to the point of annealing, what we realized that the annealing, this processing plays a very critical role. And what it seems that by annealing at 400 degrees Celsius with optimum annealing condition, the flat band voltage shift towards 0 volt, and somehow that seems to help provide a better response to the analytes. Anything higher and lower temperatures again did not give as good a performance. So then what we did, we looked at the again we looked at that same device. But now what we did, instead of having the semiconductor as a sensing layer, we now utilized a separate dielectric layer as the sensing layer, or the pH sensitive layer. In this particular case, we used tantalum oxide. So this shows the isometric view of the device, and this gives more cross-sectional view of the device with more details. And again, what we found that the interface of tantalum oxide with IGZO was the source of a problem. And this is something which I'll talk about it towards the end of the lecture. Then, but what we did, we utilized annealing in order to optimize the parameters. And then what we found was that we were able to enhance the sensitivity now to about 400 millivolt per pH. Just to tell, before we had gone up to about 160 millivolt per pH. So here again, we could figure out like what was the advantage of annealing that helped to fill the vacancies, and that gave us a better performance. So apart from giving us higher sensitivity, there was another highlight of this work that is the stability. So we took the device, a standard device, and then again tested it after 1.5 years. And what we found was that the performance value had not changed much. So again, it says that, you know what, all the processing is critical, because the processing again helps to give a good stability of these devices. Okay. What I said earlier was that when we have a dielectric, we look at the different properties of the dielectric. And one is the basic property of the dielectric itself, which can be used as for this as a semiconductor device. And another one is interaction with the electrolyte. Now, what's happened? So these are the properties which a typical dielectric should have. That is, it should have a high dielectric constant, and that is needed to maximize the capacitive coupling. Also needs to have a high band gap to sustain the operating voltage, should have low interface states for better transition characteristics, and also have a high surface density of pH sensitive sites, and that is needed for what is called a high buffer capacity. Now, if you look at any single material, will not necessarily satisfy all the requirements. For example, if you see dielectrics such as hafnium oxide or zirconium oxide and all these things, they have a very high dielectric constant, which is good. They also have high inertial sensitivity, which is again good, but they have low band gaps, which is not good. Similarly, dielectrics such as silicon dioxide, silicon nitride, aluminum oxide, and all these things, they have high band gaps, which is good, but they have a low dielectric constant, which does not help, and have varying values of the inertial sensitivity limits. The question is, if you cannot have a single material which satisfies all these requirements, then why use a single material? Why not use a stack of materials? So that and can we now utilize a stack so that can we get the best of the conditions so that we are able to satisfy these conditions? So having that in mind, what we did, we wanted to study, we wanted to utilize different stacks. So this is the schematic of the device what we use, and all the details are given here. So what you see here is the top dielectric stack, because it's a dual gate, and hence we have a top dielectric and a bottom dielectric. The bottom dielectric here is silicon dioxide, and you have a top dielectric stack here, and more details are given in the cross-sectional view out here. So this pink one, what we see here is the semiconductor or IGZO. This blue one is the silicon dioxide, which is the bottom dielectric. The green one is a top dielectric stack. And then here we have the electrolyte. So now what we did was we studied the different top dielectric stacks. In one case, we utilized only yttrium oxide. In one case, we used tantalum oxide on top, yttrium oxide at the bottom, only tantalum oxide, then yttrium oxide at the top, and tantalum oxide on the bottom. So we used 4 conditions. What is important here are 3 interfaces, and we have named them. Interface 1 is between the semiconductor and the bottom gate dielectric. Interface 2 is between the semiconductor and top dielectric. Interface 3 is between dielectric and the electrolyte. And then what we did, we made devices not only DG FETs, but also with MOS, as a TFT, and a dual gate TFT. So for all these 4 structures, we made 4 devices, which helped us get a fundamental understanding of what is happening at the interface and what are the factors which are affecting or which have a role in the sensitivity. Then again, we conducted both material characterization as well as electrical characterization. So what is shown here, what we see here, these are the XPS depth profiles for the different conditions. What I would like to show here is that if wherever you see, for example, IGZO and silicon dioxide, what we see is a reasonably good transition. But whenever we have with yttrium and IGZO, we see that the transition is not that sharp. And the same thing what we see is in other structures. So what this tells us that there is a diffusion of yttrium into the semiconductor, and that diffusion we found plays a very critical role in improving the interface, and that has resulted in giving better performance values. So what we did, we looked at the DG FETs 1, 2, and 3. 4 again did not give results because it was damaged, and we found a reason why. And then what we did, we looked at the experimental values, we looked at the simulation, we conducted simulation, and also looked at theoretical values. What we found that DG FET 2, or what we call it, gave the best result, and that was because of the interface between the yttrium and the zinc oxide, and the IGZO semiconductor. At the same time, this was a stack, and if I go back out here, so if you look at it, this was the stack with this yttria at the bottom, which is interfacing with silicon dioxide, and tantalum oxide interface with the electrolyte. So here what we see that we utilized a stack capturing the best of both. On the basis of this, we are able to get a very good performance. So same thing what we did. So this was for the top gate. Then we looked at the bottom gate. At the bottom gate, again, instead of using only silicon dioxide, we use an yttria silicon dioxide interface. And again, what we saw, this improved the performance. So from 450, we went up to about 800. So on the basis of this, like slowly, we have gone about improving the sensitivity of this particular device. Then what we did, we again compared the same thing. Instead of tantalum oxide, we took we utilized hafnium oxide. So here we wanted to utilize our same philosophy that if you look at hafnium oxide, are we able to, and we were able to get around 900 millivolt per pH. But if we use a stack, will that give us a better, even further result? So we are expecting to cross the 100 barrier, 1000 barrier. But then what was surprised, what we found that in this particular case, the utilization of a stack brought down the performance. So what it tells us that there's still so much more to understand about the interfaces. The stacks help in most cases, but not in all cases. So then what we did, so far we have been working on this rigid substrates, then we looked at flexible substrates. So now once we're utilizing flexible substrate, transferring all these things is not easy because the process changes. So what we have seen here, in this particular case, we used an ITO coated PET, and we utilized different processes. And on the basis of this, we again had some results. And we were able to get to 20 millivolt per pH. And the best results we have seen is 37 millivolt per pH, but for a different design. But we are close. And again, what we saw is that if we looked at the fabrication, like we looked at the time stability after bending and all these things which are reasonably okay. So what we might feel that, like our pH is low, but then what we saw here was when we utilize it for charged biomolecules, and I'll not go through the details out here, we went all the way from 1 nanogram per milliliter to 1 picogram per milliliter of this process specific antigen. What we found that this device was indeed able to measure it. So what it tells us is that maybe if our pH sensitivity is low, is our biomolecule sensitivity is high? That is a question which it led to us. To answer this question, let's go back to what I had in an initial slide. Simple molecule, hydrogen ion, complex molecules, a simple ion, hydrogen ion, the simplest entity. Then we have got more complex entities, which are the charged biomolecules. So there has been work by researchers where people have told that hypothesized that indeed a low pH sensitivity means a high sensitivity to biomolecular charge. So a bad pH meter, a bad pH sensitivity will become a good biomolecule, will show good biomolecular sensitivity. Then Wunderlich gave an analytical theoretical validation for this. And this expression, I'll not go through details out here, but again, to show that if our pH sensitivity is high, then the biomolecule sensitivity becomes low. So what we did, we wanted to understand this further. So again, we had a device where we charge this molecule, where we put, like we had this the semiconductor oxide, then we had a stack, we put these antibodies which are Y-shaped, then we had a bifunctional aldehydes, and we had antigens capturing the antigens. We wanted to see the results. And what I would like to say here is that, like when we plotted the pH sensitivity as the this flatland voltage shift, this is for measuring the pH sensitivity, this is for measuring the biomolecule sensitivity. Indeed, what we saw is that whatever the non-textured which had a low pH sensitivity indeed gave a high biomolecule sensitivity, and vice versa. But then there was another experimental paper which went against which contradicted the hypothetical work. And what we found is that there is a difference between our work and their work. This is the way we have now structured. We have this very oriented antibodies on surface, while the other group had non-oriented antibodies on surface, and hence their experimental work did not match with the theoretical validation, while our work matched with the theoretical validation. So what I would like to say is that there is scope. Like once we're making these devices, if it's able to measure a simple entity like a hydrogen ion, or a very complex entity like a charged biomolecule, there's so many molecules in between which it can measure. So with this, I would like to conclude the talk. Just to summarize what we have seen so far, that the ISFETs have advantages over conventional pH meters. There are several performance parameters, one of which is sensitivity, and we looked at different methods to enhance sensitivity, which included using different material stacks, using physical chemical modification, and also device designs, and I shared some of the results. And then we looked at rigid devices, then also we looked at flexible devices. And the important thing was, what we showed here was the relationship, that what was the relationship between the simple molecules, simple entities like a hydrogen ion and this complex charged biomolecules. So with this, I would like to acknowledge the work of all the people the students and the postdoctoral fellows, past and present, collaborators, and funding agency, Department of Science and Technology, SCRB, and MIT. And I would like to thank you for your attention, and I'll be very happy to take any questions.
Hello, sir.
Yes, I can hear you, yes.
My voice is clear, sir? Okay.
Absolutely.
So some questions from audience.
Sure. Shall I look at the Q&A?
Here.
Yes.
Yes, sir.
Yeah,
So shall I read out the Q&A?
Yeah. Dr. Preetham will read it out for
Sure.
the participants.
Sir, I'm reading the questions from participants.
Sure.
Okay, sir. Sir, one question that does silicon oxide has better advantage over carbon-based nanomaterials, graphene, nanoparticles, or carbon nanotubes?
See, it's not just the material, but also the manner in which the material was formed, because there are several functional groups which are there, and also size of the particles. So we cannot say that only about the material per se. So it's very difficult to compare one versus the other.
Okay, sir.
So all comes, you have to identify. So you can take a specific case of one, specific case of the other, and then make a comparison. But a very generalized comparison would not be fair.
Yes. One more question, sir. How do you ensure that the surface adsorption on wafer is even? Is there a method you use to control that to get even spread across the wafer? What is the best method to measure the layer thickness of nanoparticle coating in your device?
Yes, in fact, indeed, I mean, I would not say, you know what, like that we can get a perfect spread, but we can try to make it as good as possible. And for that, we have to understand what is happening at the interface. And what I mentioned about the interplay between homogeneous and heterogeneous nucleation. In several cases, what happens is you just have the particles physically placed on the surface. In our case, these are chemically adhered to the surface. There is chemical bonding, which again, I did because of a time concern, I did not go through all the details, but we also, after texturizing the surface, we also put through ultrasonication. And what we found that even after ultrasonication, there was no change in the particle density, which means they were very strongly bound to the surface. So yes, there are methods, and our paper has described several of the methods and the mechanisms which are needed in order to get good coating.
Okay, sir. One more question, sir. Is the sensitivity depend on the morphology of nanostructures? You use zinc oxide nanorods.
Yes.
So
morphology, yeah, see, morphology, yes. I mean, see, the point here is what we found is that these kind of nanostructures, they form defects. So now, see, there's so many, one can come up, because these are very generalized questions, because it's very difficult to compare. All we can say is that these nanostructures are forming defects, and the defects are now enhancing the buffer capacity. The buffer capacity is responsible for giving a higher sensitivity. But when you compare, we have to compare, because see, whether a nanoparticle or a nanorod, we can't say that. Ultimately, it is the defects, number of defect sites. Then only we can have a good comparison.
Now I am requesting ma'am to conclude the session.
I think there are a lot of questions, but for want of time, we are closing the session. So once again, Dr. Siddharth, thank you so much for giving such an interesting talk, and thank you again for accepting our invitation to give a talk. Thank you so much, Dr. Siddharth.
It's my pleasure. Thank you very much.
Yeah,
Thank you, sir.
Yeah, thank you. Yeah. Have a good day. Bye.
Thank you.